All right, so we are moving on to section 7, unit 7, section 1, which we are looking at the confidence intervals for means, is what we're looking at. Okay. So confidence intervals for means. Previously, we looked at confidence intervals for proportions. That was back in unit 6. So now we're moving on to means and doing our inferences with those. Okay, so here's an example that we have with a farmer on a field or in a field trying to find what the average weight of tomatoes are for his from his farm. And with this, instead of trying to weigh all the tomatoes, he's just going to take a small sample because weighing all the tomatoes could be very, very difficult. And so with this, we have just a sample of 4. Okay, so we have a sample of 4 tomatoes. The average was 110. We want to do a confidence interval at 99%. And at the very end, we're told that the standard deviation in the field was 40 in the past. So we'd assume that that would carry over to the new one. This is important for using our Z. So you can take a second, figure out what the values are, at least for your state, plan, do, and conclude. Hopefully you can at least do the state and plan. Maybe the do you might have forgotten the formula, but you can take a second, pause the video to do that. All right, let's continue. Okay, so first off is our state. So this is where we state our mean and or our variables and the level. And so the variable that we're using here is mu because we're talking about a mean here, and that is the true population of all the tomatoes. 99% means that our Z, our critical Z value is 2.576. Okay. Also in this point, you could mention the other variables that you have. N is equal to 4 because that was a sample size. X bar is 110. That was the average grams. That was the average weight of the 4 samples, and the standard deviation was 40 because that's what was told. Okay, so there's our state. Next up, we have our plan. Okay, so plan, remember, is our 3 criteria that have to be met. You also want to mention what type of test is being done. In this case, a 1 sample Z confidence interval for the means. Now, random, it is stated in the problem that you took a random sample, so that one's covered. It's independent because 4 is probably less than 10% of all the tomatoes in the field. And then it's approximately normal because the population is said to be normal. And so if the population is normal, then we can have the assumption that the sample would also be normal. Okay, moving on to do. Okay, so do, which is our point estimate, X bar, the average, plus or minus the critical value, the Z, times the standard deviation. Since it's from a sample, we have to take the standard deviation divided by the square root of the N. Okay, so that's our formula, so we plug everything in. So we end up with 110 plus or minus 2.576 times 40 over the root 4, which gets us 10 plus or minus 51.52. Or if you want to find what the actual numbers are, you just add those two together to get the upper, and you subtract them to get the lower. So either one of these, this answer here with the plus or minus, or this answer down here, will be accepted. They both are telling you the same thing, just one slightly different than the other. Okay, so there is our do step. So you see, fairly straightforward. It's just like the confidence interval we did with a proportion, but it is slightly different because of the standard deviation error or the margin of error. Our conclude step, which is just summarizing everything. We want to mention what level of confidence we had, 99%. We want to mention what the interval was. So this is where you want to use kind of the actual numbers. Okay, make sure you use your units. Okay, we want to make sure the units are being used here. And then you also want to talk about what the context of the problem was. So you were talking about the mean weight of the tomatoes coming from the plant. So 99% mean weight, and then the difference between it. And boom, you're done. Nothing else needs to be said. Okay, so there's an example of doing that. So the previous example was one that was using a Z because the standard deviation was known. Now, if you noticed in that problem at the beginning, if you want to back it up, you'll be able to see that I bolded the fact that the standard deviation was set. what the standard deviation was previously. That is not always going to be the case, and for most samples, you're not going to have the actual standard deviation because you would need a lot of data to do that. If you're just taking a sample of something, then you're probably just going to have the standard deviation from that sample. If that is the case, you are going to use what's known as a t-statistic or a t-test, okay? Because the standard deviation is a given. And the reason why we use a t-test here is because it adjusts the normal distribution curve. If you look up here at this image, the black bell curve is what a normal distribution would look like, okay? What a perfect one, in quotations, would look like. As you have a smaller and smaller sample, what happens is that you have more volatility in it. The standard deviation is larger, essentially. And because of that, we're going to flatten out this curve. So you see here, this red line is if you have a DF of 3, which means degree of freedom, which we talked about. But basically, you have a sample of 4. And the blue one is if you have a sample of 7. So as you see, if you get more and more samples, you get closer to that normal distribution curve. But because you don't have the full sample and you only have smaller ones, it's going to adjust this normal distribution curve, okay? So it is still similar to the normal distribution. It still is centered at 0. It still is a bell shape, but it is slightly, it's spread out more, which means its tails are larger, okay? So the tails have a larger area, which means we're going to have to increase our t-value to get a smaller one. So if we only wanted 5% in one tail, we're not going to use 1 point, or actually, if you want, let's use the example on here. If you wanted 0.025% on each tail, so 5% total with both tails, as you see, the 1.96 is for a normal one, but for the 6, the DF of 6, it's now 2.45, and a DF of 3, it's now up to 3.18. So you see those increase as the degree of freedom falls, okay? Okay, so degree of freedom, which I mentioned in a previous slide, is basically adjust the shape of this curve. The larger the sample size, the closer you are to it, and the way to find the degree of freedom is you take how large your sample was and subtract it by 1. You take how large the sample was, subtract it by 1, and that finds your degree of freedom. Okay. Now, using your t-table, if you look in your packet with your tables and your formulas, if you look at table B, okay, so table B is your t distribution, and it says on it t distribution. So go past the z ones, okay, that we've been using, table A, go to table B, and you'll see what you have down here is that you have your tail probability, so how much you want in this section. So if you want 5%, you would go to 5%, which is this column right here. If you want 10% here, if you want down to 1%, it's over here. So however much you want in one tail to find what the critical value is that you're going to plug in for your confidence interval. And then down the left-hand side is your degree of freedom. If you had a sample of 4, your degree of freedom would be 3. So 3, degree of freedom 3, looking at, let's say 99, so 1% in the tail means we would use 4.541 instead of 2.33 is what we normally would, or 2.575 if we're using a normal distribution. Okay, so because of a t, it's a lot larger. So that's how this table works, is that whatever you want in the tail, or the p-value in the tail, is along the top, and then you find your degree of freedom down the side, and you find that new critical value. Okay. So an example here, so using your table, if you want 90% critical value, n equals 30, okay, you would use your tail probability would be 0.05. Yeah, it should be 0.05. Okay, not 2. This should be a 5. Should be 5. 0.05. DF would be 25, which means if you look at your table, you're going to use 1.96. Now, you can use your calculator to find this value. Okay, second vars, go down to number 4, INVT, which is the inverse of the t value, and then you're going to plug in what you want your p value to be, and then what the df was. Okay, so p value, df, and it tells you your number. Okay, so take a second and find 95% for 20, for an n of 20. All right, so if you did this, you would know that your tails are 0.025. 0.025, your degree of freedom would be 19, which if you look at your table would get you 2.093. Okay, is the t for that one. Great. All right, now moving on to the next one is if we have 96% confidence level, an n of 260. So if we want 96%, that means each tail is only going to be 0.02 because it would be 4% left over and you cut it in half because each tail has to have the same amount. After that, we look at our degree of freedom. Our degree of freedom should be 259. So it should be 259, not 229. Okay. 259. And then what we want to do is we want to round down to the closest degree of freedom that we have. And the closest degree of freedom we have from there is 100. Okay, so we would round down from there. So we'd use our degree of freedom of 100, I believe. And then we'd go to 0.02, which should get you about 2081 on the table. Now, if you used your calculator, you would get a slightly different one, which is fine. Both are acceptable. Okay, so both are acceptable in this case if you use the table or the calculator. The table is, or the calculator is going to be more exact. Okay, for this. All right, so take a second and find the t value for 96% for an n of 5. All right, so with that one, you should have gotten 2.999. Okay, and that's your t. All right, fairly easy, fairly good. All right, continuing on, we have our constructing it. Okay, so if the mean is, if we're doing a mean and the sigma is unknown, so the standard deviation is unknown, the actual standard deviation. Okay. This is just an overview. You guys should, again, this kind of gets drilled into you. So like every single video and every single slide, we're going to go over this random, normal, do, and conclude, because this is how you do your steps. So random. So random assignment, if you're talking about an experiment. So if you're doing an experiment, they should talk about random assignment. If it's a selection, it should be a simple random sample, randomly selected, etc., something around there. Under normal, so if the sample size is less than 30, then make sure that it is normally distributed. What you can do, or what you'll want to do, is plot just a quick dot plot and see what the shape looks like. If it looks fairly normal, you're good. You're looking for outliers. If there's major outliers, you want to mention it in this case. Hey, when we did a dot plot, it looked like there was a lot of outliers. So if your sample is less than 30, you just want to do a quick dot plot and then see where everything is. If the sample is greater than 30, you can just use CLT, okay, the central limit theorem. It's greater than 30, you're all good. Okay, so under 30, you'd want to do the dot plot and see what it looks like, make sure there's no outliers. Over 30, central limit theorem, and you're good. Independent, okay, making sure that it's independent. So individual observations, make sure they were independent, or you could use that the 10% rule applies. Okay, so 10% rule for your independence. If any of these are not mentioned, okay, if any of these are not mentioned or not met, you want to mention it in to it, and use a warning, proceed with caution, anything like that. Okay, but then continue and finish the confidence interval, but just mention that, hey, this criteria wasn't met, but you still continue it, so you don't just stop. Okay, so let's look at this example. So we're looking at pulses of students in a class. Okay. Pulses of students in a class are taken. There's 9 of them. Here they are. And we want to construct a 95% confidence interval. Okay. So let's go through this with our state, plan, and do. Okay, so the first thing up is state. So we want to state the parameters and level of interest for this. So our parameter, or our variable essentially, mu is the average test score of our AP student. It's a 1 sample t interval test, okay, for means, so we're going to be using our t. And then it's a 95% confidence, so we go 95% on 2 tails, so it would be a 0.025. Degree of freedom was 8 because there was 9 samples, so it's 9 minus 1, that's our degree of freedom. And we get a critical t value of 2.306 in this case. Okay. Also in that case, you might want to mention the mean and the sample standard deviation, which you can find by using 1-bar stats. So L1 list 1-bar stats. So the sample mean was about 60.2, and the standard deviation, which you use SX, not sigma X on your calculator. So make sure you use SX, 7.29. Planning, random, independent, normal. Okay. So is it random? It's not random. Okay, so proceed with caution. And it's not random because they took people from the same class. They didn't take a sample of it, they just took people from a class. And so this sample could be specific to that class, not all AP students. So that's why we would say proceed with caution. Is it independent? We would say 9% is less than 10% of all AP students. Boom, got your independence. And normal, it's less than 30. And then if you look at the dot plot of it, it shows a little bit of skewness, but again, you can assume that it's probably going to be normal. Again, proceed with caution. Okay, so if it falls into that, you would say proceed with caution. All right, do. So you're doing a t confidence interval with your formula. T, which is x bar plus or minus t star, and then sx over the square root of n. So you plug in your numbers. Okay. The sx over square root of n is known as the standard error, okay, or SE, and it's used for sampling. When you plug everything in, you get 60.2, which was the mean that was calculated from those 9 points, of 2.3, because it was 2.99 or something, 2.306. You could write that all the way out. And then 7.29, which was the sample standard deviation, all over square root of 9, which gets you either 60.2 plus or minus 5.59 or 54.61 and 65.79. Right. And that would be our standard deviation, or our confidence interval from everything. And last but not least, we conclude and interpret it. So we have a 95% confidence that the average pulse of AP students, AP statistics students, okay, again, mention the level, you mention the level, you mention what the context of the problem was, is between, and then your 2 levels of confidence, okay, your bounds. And that's what we have. All right. And that's it for this one. So using a t, when we have 3 points or less than 30, standard deviation is not given, the population standard deviation is not given, we're going to need to use the t distribution. Okay, so it's just another one that you have. Okay. All right. And that's it for section 1.